So the beginning one here represents the equilibrium position, where it's not moving, there's no energy in the system, and the object is just at rest, okay? It's kind of gives us an idea of what the system looks like here. We have a spring constant of K, and the object has a mass of M. But also, and this part is important, this line that represents the equilibrium position. So this is when the object is in equilibrium. Because what we're going to do is we're going to take this object and displace it and talk about how the spring and the mass work together to create an oscillator. So although this represents at rest, standing still for all time, we're going to pull the object outwards and release it at t equals 0. So this actual set of notes is really about these 5 places, okay? This one's just our starter. Let us know what it looks like when nothing's happening. We're going to talk about these 5 places, okay? Now, before I go too deep into this, how much of a oscillation is this? Yeah? How do you know it's half?
Because it hasn't returned its original position yet, so it's like on the other end of it.
That's right, it hasn't returned to its original position. This represents 1/2 of an oscillation. I didn't put a whole one on here because I think you can probably imagine a lot of it's going to be redundant, that there's something repetitive about what happens. So we're going to talk about all of the states of 1/2 of an oscillation, and then I'll leave it to you to fill in the blanks for what happens on the trip back. Is that fair enough? Are we all good to go? All right, so let's start here at t equals 0. And let's talk about what I think you need to know about t equals 0. First, somebody or something has to displace the object, the original displacement. This represents some external thing that takes the object and pulls it back or pushes it in to get it started. This is not the only way to start an oscillator. We could have thumped it when it's at equilibrium and given it some velocity. But instead, we're doing it this way, where we're going to pull it out and let it go. This is when you did the spring mass thing for your lab, you lifted it up and dropped it, or you pulled it down and released it. You took it from equilibrium and you added energy to the system. In this case, the amount of energy in the system is 1/2 kx max squared. This is the energy you put into the system at the start. Now, the spring is a conservative force. So the spring is pulling back with a force this direction. Now, the first thing I want to impress upon you is that net force has to equal MA. Right now, this is as big as the displacement is going to get. And the force is the force from a spring, minus Kx equals MA. The minus is about direction. This is telling me that the acceleration is in the opposite direction of the displacement. So I pulled the object to the right. When I release it, the acceleration is going to be to the left. That's what that negative sign is all about. But also, and this part's tricky, this has to be the maximum acceleration because it's the maximum displacement. So this represents the acceleration at its biggest. If this were a ride and you were on it, you would feel the most force right now. You would feel uncomfortable because it's pushing you the hardest right now. In fact, we can write this as A max equals K over M X max. And I'm leaving the negative sign out because I'm only talking about the magnitude. We're talking about the magnitude of the acceleration is at its greatest when we are here. I'm leaving out the direction part. Now, there's a few other things I want to talk about, bless you. They're pretty simple. For example, at this instant, when we let it go, the velocity is 0, right? We're instantaneously at rest because we pulled it out, and this is the instant I let go, so the velocity is 0 at that instant. And if the velocity is 0 at that instant, the kinetic energy is also 0 at that instant, which tells you and me that all of the energy, the total energy right now, is all potential. This is t equals 0. What direction is the acceleration, to the left or to the right? Has to be in the direction of the force. That means it's to the left. I'm not going to draw another arrow for the acceleration, but acceleration's in the direction of the unbalanced force. All right. A few moments pass. The object has been accelerating for a few moments, and now we have a velocity. All right, something to the left, because it's been accelerating to the left. It's still experiencing a force, but that force is now less. It has to be less. The displacement is less. So we still have a force, but it's not as large as it was before. In fact, right now, that force is minus kx, where x represents this distance now, a smaller distance. That means the acceleration is also less. In fact, we can say that ma is going to be equal to minus kx, where x is now less than the maximum, so a is less than the maximum. It's still in the opposite direction of the displacement. It's still to the left. So the object is still speeding up, but it's not speeding up as much, right? It's speeding up, but it's not speeding up as much. So it's still getting faster because the acceleration is still that direction. Now, a few little things to think about. We now must have some kinetic energy because we're moving. We have velocity, so we have kinetic energy equal to 1/2 mv squared, whatever that v happens to be. And we still have potential energy because the spring is not at its relaxed state, so the potential energy has to equal 1/2 kx squared. I don't think this is a huge stretch, but if I add these together, I get the total energy, and that still has to equal 1/2 kx max squared. The total energy hasn't changed. So no energy has been added to the system or taken away. We've just lowered the potential energy and increased the kinetic energy. But the total energy still has to equal what we had at the start. And I watched somebody just squint hard. This and this have to be the same. I'm not calling that person out, but I'm looking right at him right now. We good? That's the total. You what?
Like, if you're adding k and u, why would it be 1/2 k? Like, where the energy is go?
It didn't go anywhere. What I'm saying is that currently there's both kinetic energy and potential energy, and they have to equal the original amount of potential energy. That's what I'm trying to say. So it's like when you pick something up and drop it, it starts with an original amount of gravitational potential energy, and as it gets lower, the potential energy becomes less, but the kinetic energy increases. That's what's happening.
So it doesn't, like, it's not like doing math with it together, it's just like you have to know that in the beginning is always going to equal.
Right, it's going to always equal the total amount of energy we started with. That okay? All right. All right. Now, this is somewhere in the middle. But as you can imagine, it's about to reach equilibrium. So can we go on and talk a little bit about equilibrium now? Now, when you make it to equilibrium, the The first thing you have to realize is that x equals 0. Because x equals 0, that means the net force equals 0. That means the acceleration equals 0. But it's not at rest. It's moving. In fact, this is the moment when its velocity is at a maximum. It's going as fast as it's going to go as it passes through equilibrium. It doesn't stop here. Even though the acceleration is 0, it's got inertia. So it's going to pass through here. But it's not going to be accelerating for this instant. For this instant, it's not getting faster or slower. This is as fast as it's going to go. But that also means that at this instant, the potential energy, which is 1/2 kx squared, is 0. That means all the energy is in the form of kinetic energy, which has to be equal to 1/2 k v max squared. All good so far? But the total amount of energy stays the same. So this still equals 1/2 k. Oh, I'm so sorry. Mr. Shelton screwed up. This isn't k. I was getting ahead of myself. This is kinetic energy. That's mv squared. It's been a rough day. Yeah, I'm glad I caught my mistake before one of you just made fun of me for it. But do you understand what I did there that was wrong? Kinetic energy 1/2 mv squared. I know they all look the same sometimes. Mr. Shelton must be looking forward to his after-school things. Is hoping to get there. Unfortunately, after-school time is going to be rough today. We've got to go down to the office and have a conversation. It's going to be unpleasant. But this will be x max squared. So the first, let me just point this out again. I'm harping on this a lot, but the energy is always equal to how much energy we put in at the beginning. That's where we established how much energy there was, and this is how much energy we put in at the beginning. But all that energy is now kinetic energy. Right? It's all kinetic energy, but there's an equal amount. So we have to account for all of it. So all of it has gone from potential to kinetic. But what this means for us is that we can figure out what Vmax is. We can figure out how fast it's going, because we can solve this for Vmax. And so if we do the algebra, which means cancel out the 1/2 and then divide by m and take the square root, we'll get Vmax equals the square root of k over m x max. This is just me solving for Vmax. So I cancel out the 1/2, divide both sides by m, and then take the square root. Everything okay? I want you to tuck this away for later. We're going to need it. And I want you to tuck this away for later. We're going to need it. All right, ready to go on to the next step? All right, our object passes over to the other side. It's still moving that way. However, which means it still has a velocity this way. But now the force has changed direction. All right, the force is now in this direction. Now that means it's slowing down. Right? The force is in the opposite direction. So although this is still true, minus kx equals ma, this means the x is now on the other side, so the a is now in the other direction. So now that we're moved to the left, the acceleration is to the right. But the object's still moving to the left, so this acceleration is going to be slowing it down. We're up here, this whole other part, it was speeding up. Now it's slowing down. Now it's still in the middle. So it has kinetic energy equal to 1/2 mv squared, something in the middle. It has potential energy equal to 1/2 kx squared, again, something in the middle. And all of this has to equal, well, it could equal either 1/2 mv max squared, or it could equal 1/2 kx max squared. It can equal either one of those two things. Whatever one you happen to have is what you could use. Because it can be either one. But again, we're in the middle. So we are slowing down. All good? Any question about that? So again, we are some distance x on the other side, the negative side if you'd like. Over here, we'll finally come to rest again when we reach x max. Here, the velocity equals 0. It has been stopped. But this is also the largest that the displacement will be, which means we are back to being at maximum amount of force. This is where the force is the biggest. So if you're actually here, the force you're experiencing is the greatest it's going to be. Force is at a max. That means the acceleration is also at its max. But the velocity is 0. There is no kinetic energy. But our potential energy is back at being at the max, 1/2 k x max squared. But again, this is when we are stopped. But we're only stopped for a moment. Then the object turns around and goes back. So this happens in an instant, and then we go back the other direction. And the cycle repeats itself. So we've stopped for a minute, but now we're going to start speeding up again. This whole thing is about speeding up and slowing down. Speeding up and slowing down. It goes over and over and over again. So what you have is how the energy and force is related for all of these. Direction is important. So in the beginning, our displacement's to the right, so our force and acceleration is to the left. That occurs till we get to the middle. When we get to the middle, force is 0. But as soon as we cross the other side, the force and everything changes direction. We're now slowing down. Now that we're stopped, this whole thing's going to start the other way. We're going to start speeding up to the right. So my question for you, my first question for you is, when does this happen? Like, how much of a period does it take to get to here? Okay. A quarter. If this whole thing represents half of an oscillation, then this must take place at half of the at 1/4 of the period, because this is a quarter of the way. How much of a period is it here? Go ahead, Allie. You said it.
1/2.
Yeah. So that's to be 1/2 of a period. All right, now look, hear me really closely for a minute. This one right here, from here to here, or from here to here. If you think about what this is, the first one is what would happen if you had like something that could launch an object. If you launch it, you pull it back and let it go, and it leaves the spring when it makes it to equilibrium. Or how many things have we had where a car goes down a hill, hits a spring, and the spring brings it to rest? Those problems sound familiar? I hope so, because this one is launching, and this one is stopping. It takes 1/4 of the period to launch something. If you want to ask how long does it take to launch something, it's 1/4 of a period. And it takes 1/4 of a period to stop something. So something rolled down a hill, hits a spring, and stops. How long does it take to stop? 1/4 of the period. You calculate the period, calculate 1/4 of it. You calculate the period, and 1/4 of it is how long it takes to stop. If you launch something, well, calculate the period. 1/4 of it is what it takes to start it. So every time we've launched a car, or every time we've stopped a car using a spring, we could have figured out how long that took. We couldn't have done it before because you can't use a motion equation for this. Right? We have to use something else because motion equations only work for something that has a constant acceleration. And what I can tell you here is that the acceleration is constantly changing. Right? The acceleration is either speeding up, or is getting bigger, or getting smaller, or zero. Right? Everywhere in here, the acceleration is zero. Everywhere here and here, the acceleration is at a maximum. So everything about this is always changing. You got a bunch of notes there, right? Now, on Friday, if you'll recall, and I hope you do, we were talking about x as a function of t. Do you remember that conversation? We came up with an equation for that. Do you remember? Do you have your notes? Can you look at them? That'll help, especially if you're awake. Awake helps the most. Go ahead, Aaron.
Just the equation.
Sure.
X max cosine W thing.
The W thing times t. Yeah. Now, the W thing is our generic term for the angular frequency. It stands for things, and we talked about the fact that it stands for things, but most importantly, the W thing for the spring mass is square root of k over m, but it's something that's going to be physical. It's a parameter. It's something that you can measure. So in this case, it's the mass and the spring constant. It's something physical about your device. For a pendulum, we know it has something to do with the length of the pendulum. So this is going to be something that controls how it moves. We just use this omega there because it's a nice simple symbol. Now, if you'll recall, we did more than just this. We also talked about v as a function of t, right? Remember doing that in class? And showing what that was. We said that this was related, but they were slightly different. What was the velocity function dependent on? That should be in your notes from Friday. Did we get that far? If we didn't, it's okay. Because I didn't know if we got that far on Friday or not.
We didn't finish.
State, and if you don't see this, you're going to have to kind of pick it up. That it looks to me like the velocity would be based on the sign. And if the position is based on the cosine. And it's more than that. This whole thing was about telling us that the position and the velocity are always kind of in the opposites. Well, that means that I need something. I need a negative here. Something to tell me that the velocity and the position are going to be doing opposite things. Now, the last thing I want you to look at, same, that means this must also be omega here, because that's the thing that controls the period. One last thing. This has to be the number that represents the maximum velocity. Right? This is going to be oscillating between velocity max in one direction and velocity max in the other direction. So do you have something that we can put here that represents V max? Look at your notes. We just did it. It's right there. You have to look just to the left in the little page that I've written there. What is it? Go ahead.
Square root of K over M X.
That's right. Square root of K over M X max. This is the motion equation for velocity. Okay? Has to be. Although that little XM is pretty rough. Don't make fun of it. He's trying his best. Now, I hate to say this, but we could just write omega there instead. It'd be easier. Do you see that? There's absolutely no reason why we couldn't write this as minus omega xm sine omega t. That would be just as good, and it'd be nice and generic. Now, let's turn that off, that velocity one off, and just leave the position for a minute. But I want to compare it to the acceleration. If we're going to do this, we're going to do this for all of them. This is the acceleration. It's the purple one. Now, so based on that picture, I think it's got to be cosine. But did you also notice, and I think this is important, that they're inverted? When the position is positive, the acceleration is negative. Right? So all that means is put a negative sign there. And do you have something that could tell you what the acceleration would be for its maximum? Allie, what is it?
Square root of, a equals k over mx.
Yep, that'll do it. However, of course, you know me. We could remember that omega stands for something here, and we could write this as a generic omega squared, xm cosine omega t. So specific to a spring, generic, generic. All okay? The reason why I'm emphasizing the generic is something that's really important and it's difficult to grasp. And we will not get it all in 6 minutes, but we're going to get very close. So look, I'm going to hit the... I said that this comes from a spring, right? This is a mass on a spring. So that meant that we have an unbalanced force that is causing an acceleration. This was the mass on the spring. There's several details here. The spring is what we call the restoring force. So that force was minus kx, and that equals ma. Our position function and our acceleration function are related. They're related here. But this is everything that's required for there to be an oscillation. What I mean is your acceleration has to be proportional to a negative sign, something about the restoring force, something about the inertia, times position. If you ever get a relationship that looks like this, it will oscillate. And I want to be very clear, it will be a simple harmonic oscillator. I mean, if you have something that has a linear function like this, where the force gets bigger with position, it will automatically produce an acceleration that will always cause simple harmonic motion. Always. So when you're studying forces, if something looks like this, it's an oscillator. People study this because if they see stuff like this when they're like building a building and they see something like this in their analysis, they know their building is going to oscillate. Do you think you want your buildings to oscillate? Do you want to be in a building that feels like it's bouncing up and down all the time? Not unless it's for fun. It's very unnerving. You want to experience this? Go to International Plaza, or any two-story mall will do, but International Plaza does it really good. And just stand on the balcony overlooking the downstairs and hold the balcony, close your eyes, and just wait. You'll feel it bouncing. Because as people walk, the whole thing oscillates. It can be incredibly unnerving. And if you have vertigo, you'll find out right then. So please hold on to the handrail because it'll make you nervous because all of a sudden you'll get dizzy. Now, I want to prove this to you, but it's hard to do so. So I want to try, okay? I want you to think about the only other oscillator we've talked about. And that's the pendulum. The pendulum has a mass at the bottom and some kind of length here, a string or a rod or something. When I displace it to the right, it experiences a torque back to the left. I've actually drawn it to the left, and so it's going to experience a torque back to the right. Realize I'm standing kind of in the way of some of you, so I'll move. Again, I want to see something that looks like this. So let's start by doing things that we know. There's a force here, correct? and that would be mg. And can we agree that this angle will also be theta, right, from geometry? Well, torque is R times F times the sine of the angle. So here, that's L times mg times the sine of the angle. That all good for you? Okay. Net torque equals I alpha. Now, our torque is L mg sine theta, but it's negative, meaning it's going to cause it to move in the opposite direction of theta, right? If we move theta to the clockwise, this torque is counterclockwise. This has to equal I. This is a point mass. Do you remember how to find the moment of inertia of a point mass? Mx squared, that's right. Except m this time is L, because at the end of the string. Now I said to you guys, if you have an acceleration that is proportional to a displacement, it will oscillate. We have an acceleration and we have a displacement. This thing must be an oscillator. Let's see. Alpha equals minus something over something sine theta. The top part of that something is LMG. The bottom part of that something is ML squared. You see how the M cancels out, right? You see that one of the L's cancels out? Does this look like the omega part for a pendulum? Anything where the acceleration is proportional to the displacement gives you the oscillation stuff. All right, thanks for humoring me. So the red one represents the velocity. What happened? But clear to you that when we're at the top of the one function, so when we are looking right here, that we're at the middle of this function there. Now, I'm trying to put this out there. The red line is the velocity and the blue line is the position. So seems to me when we're at the maximum velocity, we're going through the equilibrium of the position, right? Do you see that's in the middle of the position one? Now, does that continue? If I go through, say, the point where I'm at negative maximum velocity, it's like right about there. Would you agree? So this looks like the point where we're at the biggest negative velocity. Is it clear we're in the middle of the blue again? All right, so the first thing I want to do is establish, isn't that what we talked about? When we're at maximum speed, we're at equilibrium. Is it also clear to you that the red stuff is also sinusoidal and the blue stuff is sinusoidal, but they don't line up perfectly, do they? It looks like when the when the red function is a maximum, the blue function is at 0. Does it also look like when the blue function's at a maximum, the red one's at 0? Let's take a look at that one. That might be harder to see, so let's do our best. All right, so that green line, does it look like it's at the part where blue is at a maximum? Does it look like the velocity is at 0? And the velocity is the red one, so here's where the red one is at that moment. So how fast is the object moving at that moment? Yeah, almost 0, but it's at the maximum displacement. Now, remember, this is when cosine of the angle is equal to 1, and this is when sine of the angle is equal to 0. Do you see that has to be true too? I think we can talk about the velocity by talking about the sine function. Because whenever a sine function is 0, cosine is 1. And whenever cosine is 0, sine is 1. And that's what this is showing. When cosine is 0, sine is 1. when the cosine is 1, sine is 0. So I think we use the red one is the velocity and the blue one is the position. I think we can. This part's going to be harder, so I really need you to kind of lock in for a minute. All of you who are all sleepy, got your heads down, and just so tired. So let's get rid of all this extra stuff I wrote in there. And I'm going to get rid of these green lines for just a minute. Okay, look here for just a minute. When I go from here to here, right, that's going from the biggest negative to the biggest positive. Do you notice that the whole time that that's happening, the velocity is positive? Do you see that? Because that's from here to here. Now, I want you to realize this. When the displacement's negative, the velocity is positive. Do you see that? Now let's look at, say, I don't know, starting at the positive and going towards the negative. That looks like the velocity is always negative during that time, right? That means when the object's in the positive displacement, the velocity is going backwards, or is going to go backwards. And when the position's in the negative part, the velocity is going to go forwards. Is the period the same? Is this distance the same as this distance? Do they look to be the same period? Now we can measure it. So let's try it. That goes from, it's hard to find. That looks to be at 3.1 seconds to 4.1 seconds. Looks like 1 second to me. Let's do the blue one. The blue one right there at the top is at 2.18 seconds to 3.17 seconds. That sounds like a second to me. So I think the periods are the same. If the periods are